Hello, today's lecture is going to be about buoyancy. So, this is the last section of chapter 2. So, now you can go and complete the homework on chapter 2. When a stationary body is completely or partially submerged in a fluid, the resultant fluid force acting on the body is called the buoyance force. So, buoyance force is kind of meaning that the force trying to push an object out of a fluid. So, why now there is a question why we need to calculate that or why we need to know about the buoyant force. So this is actually a really useful definition, and because for example when we have a boat on a sea and the engineers try to design a boat, they need to know whether or not a boat will sink. So this is when we use the buoyant force. So uh, basically the buoyancy is just estimating the buoyant force on a submerged object. So by the so if we consider this object here, let's say just put a star here, this object which is in a fluid, which here is fluid, right? And then here is a free surface, right? So this object is completely in the fluid, so we call this one as a completely submerged body in a fluid. And then if we look at this shape right here, some part of the shape is out of the fluid, so we call this one as partially submerged. Oops. Partially submerged, right? So let's just be systematic about it. We want to figure it out what the buoyant forces is. How can we can calculate that? So let's the object that we choose here, which is this object, right? It's a body of arbitrary shape which has a volume. So the volume of the object, which is, let's say that this is the object, so I'm just trying to write everything here, then we have more space there. So this is the volume of our object, right here. And then let's also, if we look at here, right, we have h1 here, h2 here, and then this height gonna be h. So h is going to be h2 minus h1, right? So we're gonna include the body in a parallel pipe and then draw a free body diagram of the parallel pipe with the body removed. So note that the forces that I'm trying right now to show you on the body is actually to be simplified. We add the forces gonna exerted on the plane surface of the parallel pipe, right? So let's start to show all of the forces that I have and also show that what assumption that we're gonna have in this question. So let's first start with the assumption and what we have. So first we know what is the volume of the object, right? And also we know the height of that parallel pipe shaped, right? And then also let's say if this if I extend that parallel pipe shape right from here, let me just draw it here. Okay, I think okay it's better if I draw that parallel oh sorry, okay, let's draw that parallel pipe here. Okay, if this is, let's say this is the arbitrary shape, right? And then if I go through the pages, this is going to be your parallel pipe shape. So then if this is H, right, we're gonna say that this is also AS. Then we need it when we want to calculate our forces. So let's say that we have that, and also for assumption, so we already know that we are still in the static in the fluid static. So we're gonna have we are in fluid static, we are in fluid statics. Let's say that the specific weight or density, we talked about it in the previous section, is constant. And then the other thing, we also it's better we always use the, not always but most of the time, I always using the pressure gauge. So these are also our assumption, and now it's time to have our free body of diagram, because we have to figure out what all of the forces on the shape that we have. So let's talk about it. So in the previous section, when we have a body in a fluid, we know that we have some there are some pressure that acting on the bottom of this shape, so we can call it P2. And also we're gonna have, actually we have the pressure from all sides of the body, right? So we're gonna name this one as a P1. And even we have pressure from the right, we're gonna call this one P4. And we have pressure from left to right, we're gonna name this one as P3, right? But we are trying to show the forces, but P is pressure. So we need to multiply them by the area. So we already write down AS here, right, which is the area for the top and the bottom of the shape. So these are gonna multiply by AS, P2 and P1, and P4 and P3 gonna be multiplied by the area of the, let's say, right and left, which are the same, right? So this is the area, the forces that we have. So but the these forces, let's just me write it down here as well, the name of them. So the pressure actually acting all on all the forces. So this is gonna be P4, let's say that AR, and this is P2 AS, and this is P1 AS, and this is P3 AR, right? So we have that, and then this is the weight, and we already I already said that we need to exert it. The force is going to be exerted on the plane of the surface. So this weight gonna be the weight of the fluid, and by the fluid I mean that if we call it shaded object or whatever, so this is gonna be the shaded volume, right? And FB that I just draw it here, so FB is the force that the object exerts on the fluid. So kind of, let's say, F of the body, right? So these are all our forces that we have, and now we need to choose a model to so we need to choose a model, and pick a model somehow that we can use it to relate all of our forces, for example the weight, the pressures that we have, to the other forces that we have. So we're going to use the Newton law. So it's F equal to ma, and we know that, okay, let me just write it down. Okay, sigma F equal to ma, and we know that this is fluid statics, so this is going to be 0, so this is the whole thing is equal to be 0. So, and just pause the video, I think, and try to write down the energy balance for each of the direction for x. So we need for just to make it simple, we just ignore all of the forces from the x direction. So we just we don't show the forces in the x direction basically. So then we're gonna say that sigma F in x direction is 0, and then sigma Fy, right, is equal to 0 also, which is equal to, we have F1, which is the direction is down, so it's gonna be, oh sorry, this is y. So okay, let me just show you where is y and z. Okay, if this is, okay, this is y and this is z. So for in y direction, let me, okay, it's a bad way to show it. So this is y direction and this is z direction, right? So for y direction we have F1. Oh, I'm sorry, I don't know why I just mixed them. Sorry about that. So this is z direction and this is y direction. So for y direction we have F3, which is going to the right, so it should be positive. And then we have F4 F4, that the direction is going to left, so it's going to be negative. So I write it down, and then it means that F3 equal to F4. And we also basically could just figure it out, even if we don't need to write down the balances, because if we look at the object, let me just change the color. So if we look at the object here, right, so if we from the left hand side, it's all of the pressure that you can see, they are all in the same direction. So if we say that this is right, this is left, and this is right, let me just show you, and this is P4 and this is P3, because they are in the same elevation and it's fluid statics, then P3 and P4, they are equal. So the area that they are acting on are also the same. So it means that F4 and F3 are the same. So let's go to write down the balances in Z direction. So this is forces in Z direction. It doesn't have the vector bar here, sorry. So Fz, so this is also equal to 0. And what we have F2, which is positive, we have F1 negative, we have weight, and we know that this is weight of the shaded volume. And then also we have F of the body or buoyancy. So this is what we have. And if we are trying to find FB, right? So let's solve it for FB. So I'm going to make it I'm going to simplify it. So F2 minus F1 and minus weight of the fluid, right? So let's elaborate what is F2 and F1 and what is F of the fluid, right? So if I write it down, we have F2. Okay, let me just write numbered all the equation that we need. So this is equation number 1. You can also do that when you're taking your exam and doing your homework. It's make the life of the grader easier. So FB equal to F2 minus F1. So we have it here, so I don't need to rewrite it down, right? So okay, now for F2, I show you before that F2 is P2 times AS, F1 is P1 times AS. We are trying to find F2 minus F1. So let's substitute them here. So for F2 we have P2 times AS, and for F1 we have P1 times AS. And if we factorize AS, we have P2 minus P1 and times AS. And from the Pascal law that we talked about it in the previous section, we know that the P2 minus P1 is gamma H, right? And I show you the H here is H2 minus H1, right? And then if we just plug it in this one into the previous equation, we're gonna have at the end F2 minus F1 equal to gamma H2 minus H1 times AS, right? This is another equation that we have here. So we're gonna call it number 2. And this is the other one. Okay. And now we need to know what is the weight of fluid, right? So weight of the fluid means we need to know the m of the fluid of that shaded part times g, right? And we know that m is going to be rho times the volume of that shaded body, and we have a g here, so we're gonna write it down. And we know that I accidentally deleted. So we also know that rho g is gamma, so we have gamma times of the shaded volume, right here. So basically for the weight of fluid, we have gamma times the volume of shaded body. So let's number this one as equation 3, right? And now in equation 3, we need to know that what is the volume of shade. So if I write it down, the volume of shade, so let's just write it down this way. So for calculating the volume of shade, we need to know that the total volume and the volume of the object. So we already know that the volume of the object is the volume that it's given in the question, and then for the total volume, I already show you here, this is AS, right, and this is H. So the total volume gonna be, if we call it total volume, it's gonna be H times AS, and we know that H is H2 minus H1 times AS, correct? So also, if we call the shaded volume as, let's say, volume of the fluid, now we can subtract the total volume from the volume of the object, and we can find that. So the total volume minus the volume of the object equal to H2 minus H1 times AS, right? And minus the volume of the object. Now, if we call this equation number 4, this one, equation number 4, we need to plug in number 4 to 3, and then we can find the weight of the fluid for that shaded region. So we have gamma, and the volume of the shaded region gonna be H2 minus H1 times AS minus the volume of the object, right? So let's call this equation number 5. So now we know both of F21 and the weight of the fluid, so which is the equation number 5 and equation number 2. So let's plug these two on equation number 1, right? And when we do that, we're gonna get FB equal to gamma H2 minus H1 times AS, and minus the weight of the body, which is gamma H2 minus H1 times AS minus volume of the object, right? And if we simplify that, these two gonna cross out, right? And then we have at the end FB is equal to gamma, oops, gamma times volume, right? And then we're gonna gamma times volume, and we know that this, oh, again I deleted. So this gamma is gonna be the fluid displaced, and this is the volume displacement. And then the other thing that I wanted to mention is that it's always acts upward. So FB is a up force, correct? So this is the important formula we need to know in this section. So we need to know that. And yeah, I think that's it for here. Let's go to the, and yeah, this is the thing that I just mentioned. The direction of the buoyancy force should be, I mean, in which the fluid gonna be out of the body should go out of the fluid. So, and the next thing that I wanted to talk is the Archimedes principle, which said that if the buoyancy force has a magnitude equal to the weight of the fluid displaced by the body, is directed vertically upward. This is what I just said. So yeah, I think that's it, and see you on the, I think, next office hours, which is tomorrow.